All right, everyone. Thank you for being here today. I am Monica Beckwith. I am a Java performance engineer. I lead the Java group, the JVM group at Microsoft. Right now, my concentration is JVM performance. So today, I'm going to talk about ilities of software engineering. Basically, these are the qualities that you would need in your software, and these qualities go back beyond functional. So any functional requirements that you have, you can definitely have them drive your software. But if you do them without the qualities that I'm going to talk about today, then there's a lack of innovation, and more so, you will have all the problems that you heard solutions for during this GeeCON, right? From day one, we heard about so many different performance, scalability, all these issues, and those are the ones that drive software innovation forward. In this particular session, I want to concentrate on JVM Java performance. Okay, so it means the language, the virtual machine, and garbage collection. So I was in the session, 2 sessions prior to this one, and Jakub showed his cats. And I thought everything went perfectly from there. I had a smile on my face. So I was like, these are my pets. I have more cats. I have 2 17-year-olds. They're almost 18-year-olds, the ones on the right corner over there. And then I have kittens and dogs. And I have some more chickens and everything else. So I'm so glad that this brought a smile to your face, because that's exactly what I wanted. If you have any questions throughout this session, please go to Slido and start typing them right now. You can also reach out to me on Twitter after this session, or any time in your life if you have any software performance engineering questions. I also do hardware. I worked for AMD, ARM, worked with Intel, Oracle, Sun. So I have some experience on the software and hardware side as well. So I wanted to talk about the agenda in a way that tells a story of what this presentation is about. So I'm going to discuss non-functional requirements, and I'm going to drive it from the performance and then the scalability angle. And the way we're going to do it is we're going to architect a garbage collector so we can see the performance. And the scalability, we're going to look at scalability in the cloud. Okay? And then I'll have some awesome quotes at the end. From my Miyagi, so Kelly's session, she talked about Miyagi, so I have a lot of Miyagis, and I am Miyagi to a lot of people too. So let's start at the very beginning. We're talking about software engineering, and when we talk about software engineering, there are 2 components. There is the stuff that we are building, the what, right? And how do we build it? So that's the other aspect of it. So the what we know, because that's captured in the functional requirements. The how do we do it, that we need to discuss and come to an agreement. The what is called the software design and development, and you have a life cycle. Like people know about the software development life cycle. The how is the architecture. So you also need an architecture document. The document that talks about the requirements, the agreement between you and your customer. So naturally, the left is known as functional requirements, and the right is called non-functional or ilities. So you may be wondering, what are ilities, right? Why the term ilities? So I looked up the dictionary edition of that, and it's an abstract quality that good software should exhibit. Now, what does that mean? Again, it's an abstract quality. So quality is something that your customer appreciates out of your software. Yes, you meet the functional requirements, but can you deliver the quality that the customer is expecting? So these terms, these ilities, define the quality and the expectations of your customer from your software. So let's look at these ilities. I'm not going to cover all of them, but I'm going to list a few of them here. Performance, so we will talk about that. Security. Now, for example, of course, your functional specifications will have the security protocol and everything else. But if your customer is expecting a TLS, like a transport layer 1.3, and you design it for 1.0, then there is some miscommunication there. So, and you may have to change your functional requirements based on that. So let's get those things documented, and those are the ilities of their software for that matter. I'll talk about scalability. Usability as well, I'll talk about it later. We'll talk about portability very quickly. And the last thing that we'll not talk about is observability. And observability is very different from monitoring. Observability is something that gives you a peek into what your system is doing, your software system is doing, and it's from the workload that's running. So it's from the perspective of a driver, an external driver, and you can observe your software. So for people that are working with Java, they know the JFRs, right? So the JFRs are something that gives us observability into what the virtual machine does, what the GC does, what the JIT compiler does. So it's an overlook into the internals of your software. So most often than not, I'll be covering two things of an ility, the what and then how. Okay? And let's dive into performance. Let's talk about what is performance. So if you go and ask your customer, hey, do you have any performance requirements? What do you think their answer is going to be? Their answer is going to be, I want everything to go fast. Like, how many times during the presentations yesterday, people talk about performance in terms of fast? Like, is that a definition? Because I know everything wants to be fast, right? Well, what is this fast? What do you mean by fast? So that's what I mean by non-functional requirements, because fast can be calculated and in terms of non-functional requirements. So instead of giving yourself the headache of assuming what fast is, we go and do some tested methodology. So we gather the stakeholders, your customers, and then we define success. Like, I understand fast, but what is success to you? And these are also called SLA, service level agreements. So let's look at that. So define your success criteria for your performance requirements, which are also known as your SLAs. And these SLAs are very clear to your customer. They just need to communicate it to you. Okay? So how do you define success or SLAs for your performance, right? So you can define it in terms of footprint, which means how much, say, memory does your software need to execute? This footprint could also be, like if you're scaling, then it would be how much scale, like the physical footprint, your software needs to be able to execute. So you have a database that's sharded, so that's your footprint. And so many things can contribute to footprint, right? Footprint also becomes a side effect of performance optimization. And I will talk about it when I talk about performance a little bit deeper. Next is response times. This is the responsiveness of your application, okay? And we will dive into that. And then comes throughput. So throughput is always operations. How much can I push the system, and how much can it deliver, right? So you don't want to bring the system to its knees. So there is also some tertiary terms that I want to include here. Capacity of your system, and then utilization. There's always a utilization factor in your system. If you cross even 1% beyond the utilization factor, you will see serious issues. Your system performance will nosedive. And we'll talk about that in terms of the laws that are behind that, okay? The thing that I'm not going to talk about, and a thing that keeps getting mentioned with performance, is availability. So availability is the uptime of your system. So, and if your system does go down, then how much time between failures? So the mean time between failures and the uptime of your system, that guarantees your availability. And people, especially in critical sectors, they try to achieve an availability of 5 nines, basically 99.999. Okay? So we'll cover two things, throughput, and response times. So this is your application timeline, and your application is doing its work, okay? As it's working, it gets a stimulus, right? So basically, the stimulus is sent right now at T0, and your application does its work with the stimulus in place, okay? And that's called continuing its work. And then finally, at T1, it gets done with its work, and then it can send a response back. So basically, what I'm showing here is an application's responsiveness. Basically, you receive the stimulus, and then you can send a response. So if you have been to Andre's talk yesterday, he was talking about responsiveness in terms of startup, cold start, right? So you could think of T0 is your cold start, and then T1 is when your application is ready. Now, this readiness would mean something different to your customer, so make sure you're clarifying what the readiness means. Do you mean that you're in the ramp-up phase, or you're at the beginning of ramp-up phase, or you're done with ramp-up phase? That means, are you in the steady state? So, but at this point, we're just looking at responsiveness, right? So your application sent a response at T1. Now let's look at the same application when the stimulus arrives. It's doing its work, but unfortunately, it has a pause or an interrupt, right? The application stops working, literally, okay? So let's call the work that it didn't complete the work, right? So let's call the work that it did as ACW0, and then it continues its work, and unfortunately, it's interrupted again, and so on and so forth. So now the same work that it did in the first time without the pauses, it takes up to T2 seconds, let's say, and it sends a response back. This is, just for reference, T1 is right there where the second pause happens, okay? Now, because of the pauses, you saw that the responsiveness of the application was delayed. You got the response later on. Now, same applications, we'll compare A and B, and we'll talk about them in terms of throughput. So I'm trying to establish a relationship between latency and throughput, okay? But how we measure or how we calculate them is different. So you have the two applications. Left is A, right is B. And let's define throughput. So throughput is, like I said, operations per second, right? So I'll define it in terms of work done. Whatever your work was, if you're a database, then it could be response per second, or it could be transactions per second, right? So this is the work done. So from T0, when you receive the stimulus, to the T1, when you send this response back, that's the amount of work you did with respect to the stimulus. So work done is basically ACW, that was your work, divided by time. So operations per second, right? So divided by the time it took you to get the work done. What happens to the other one, the application B? So remember, we're measuring the same time period, T0, T1, to be able to compare them. Application B, unfortunately, could only do part of the work between T0 and T1. It could only do W0 and W1 work when you're comparing them on the same time period, right? So what do we know? We know that ACW0 and ACW1, the work done, is less than ACW. Because remember, at T1, application A was able to send the response back, but application B needed until T2 to complete its work. So the work done is less. So basically, the throughput is less. So that is how we measure throughput. So we keep the time axis as constant, and then you see how many operations can be pushed through, right? So there is a difference of methodology in the way we talk about throughput and responsiveness. Now, with that in mind, let's dive into how we do performance. So the way I would like to talk about the how is by architecting a garbage collector, okay? And we all will be architects by the end of this talk. So I want to talk about a very simple fact of garbage collectors. And this is true with all garbage collectors, right? Throughput and latency are the two main drivers for refinement in garbage collector algorithm. Now, what do I mean by that? So basically, what I was talking about earlier, like when you have an interrupt, when you have any stoppage to your actual application, those are the two things that your garbage collector needs to understand and needs to improve on. So again, what does that mean? That means that the garbage collector needs to get out of the way, either as soon as it can, or as in parallel, like as many resources it can utilize, and then finish work and then get out. So there are two different ways that the garbage collector can work. So let's look at that further. Here's a simple GC. We talked about the GC work, right? What it does actually, and then we all know the weak generational hypothesis. Basically, we're going to assume that weak generational hypothesis is true because that's what we have seen in OPENJDK. So what that means is that most objects die young, right? So and then anything that's long-lived is like really small. So we can take care of this weak generational hypothesis, and we can have a generational GC. Now, what if your customer comes and tells you that I want my GC to be maximized for throughput? So now we'll go architect a throughput maximizer GC. We talked about the weak generational hypothesis, so we'll go with generations. Now, for example, if it was not the young and old generation of OPENJDK, if you had like multi-generation collector, then your generations would be called multi-generations, right? So it'll be Gen 0 onto whatever. So some people use the generations for large objects as well. So say, for example, in case of ZGC, the larger objects or medium-sized objects are kept in a separate area, okay? Now let's design a cloud around what generational, since we're architecting, let's design a cloud around what generational collector would need, right? So I said objects die young, right? So we have to make sure that it's feeding the applications, and the applications are understanding, and they're kind of like allocating in a way that most objects die young, right? So we can take care of the allocations as long as they can die young. Then the garbage collector has to promote mostly long-lived objects. So the garbage collector has to be sized and designed to be able to, say, automatically resize itself so that only objects that are long-lived are promoted. So this kind of ensures that small, long-lived data sets are in the older generation. Because we have generations, we have something called maintenance barriers. And remember I said I'll talk about footprint when I'm talking about garbage collectors. So even though we're designing for throughput, remember that when you have a generational collector, you do have maintenance barriers, and that adds to your footprint. Because we're doing throughput maximizer, the type of GC work that we want to do is called parallel work. Basically, it means you stop the application, you do all of your GC work in one sitting, and then you get done and get out and let the application go ahead. So if you think about the application A, if it had a stop the world pause, like a single pause, it would just be a singular pause. It'll get done and get out of the way. So what do we need for parallel work, right? I said that we need all the threads to get done in a pause and get out of the way, which means I'm not looking for concurrency, right? And what else? I mentioned pause, so of course pauses. I also said lots of threads. Now what do all these threads do? There is this whole concept of task queues, basically queuing theory. You have task stealing. And one of the things that you have to know is these threads are working. They're not paying attention to the application. They are just trying to keep their heads down, do their work, and get done, get out. Unfortunately, sometimes, the garbage collection has such an overload that it may not be able to get done with its work, which means that it is now stalled. The application is now stalled. So for such periods, we need something that we can fall back to, right? And that's called the fallback GC, and this avoids evacuation failure. So if your your garbage collection cannot evacuate on time, then you fall back to a fallback GC. Let's look at low latency optimized. So I want my garbage collector to be optimized for low latency. Basically, I want to be able to have the least amount of interrupts, okay? And the garbage collector can run in the background. So we know it's generational, so we'll keep all the generational stuff right there. The work units now need to be finely controlled because we need a garbage collector to be not there, or at least we shouldn't be paused to know that garbage collector needs to work, okay? So let's build a cloud around that. The way we achieve that, and I'll give you OpenJDK examples, is through regions. So if you have generations, then the young generation or the old generation is the granularity of work. But if you have regions, like for example in G1's case, it starts from 1 meg, you can literally add a single region, a 1 meg region, to your collection and call it done. So you have that granularity, and that's what gives you the tunable working units. What else do? We don't have to collect everything. Like I said, a single region can be collected. So that kind of thing where we're moving regions or moving live objects, that's called compaction. And we can do it just with a single region in your compaction cycle, right? And I also said that we don't need pauses. So what is the way we can do this? Your collector can work in the background of your application. So that's called concurrent work. And there's another thing that we can do is, again, incremental. So you're basically looking to control the GC cycles, and you can do it in an incremental way. Now, there's a different problem to solve, right? Because your garbage collector is doing all of its work in bits and pieces, you can say. What is the problem if the garbage collector cannot complete and cannot free space? Then the one way garbage collector can do is ask the application to back off. It's like, hey, I am still doing my GC cycle. You can back off, or you can help me. So the whole thing of backing off or helping is called graceful degradation. So with that, we also need maintenance barriers. Because anytime you have any kind of concurrent work, you need barriers. So if I just the 2 GCs that we designed, if I told you that they actually exist in OpenJDK, the throughput maximizer on the left is your parallel GC, and then on the right you have ZGC and Shenandoah, right? Now we were at the keynote, and of course there was a discussion of the default garbage collector, and we were talking about G1GC. So I have not mentioned G1GC anywhere, and that's because G1GC fits right in the middle. So it is kind of something that gives you throughput because it has stop-the-world pauses, and it does the compaction in a stop-the-world format. But it also does incremental marking. It has concurrent work as well. So what it gives you is kind of best of both the worlds. So if you don't need a maximizer, like towards the left extreme, or you don't need a very low latency garbage collector, which is towards the right extreme, that's where G1GC fits. And that's why G1GC is your default right now in OpenJDK. So let's look at the next thing. Let's dive into scalability. So again, you ask your customer, what does scalability mean? They'll very quickly respond back. Like, I think I'm maybe scaling up or maybe scaling out. I'm not quite sure. So what does that mean? Like, of course, you cannot be able to, you're not guessing. So what we need to do is measure, right? And the way we measure it is I'll show you in the following slides. But before I go into that, I want to define what scaling up and scaling out means. So, and I want to say that in terms of pros and cons. So scaling up means you're going to a bigger system. A bigger system hopefully has more resources, and it has more processing power. You also get higher bandwidth. You will also get good spatial locality. So when we're talking about hardware in one of the presentations, they talked about caching. So when you're talking about caching, the hardware has its own cache. As you go to a bigger, beefier system, your hardware cache becomes beefier as well. And you get a lot of spatial locality with respect to your data. Well, the con is similar in the sense you went bigger, you went larger, but what if you had a random access database, right? So because these CPUs are designed to optimize your data spatial locality, when you have something that needs non-uniform access, then you can have temporal issues, right, with respect to the locality. The best thing about scaling up is that almost little to no configuration is needed, right? Because you literally can take your application from a smaller system and move it. It's a lift and shift, and you're done. But if you think about it, because you have a monolith almost, right, your bulk may be having issues. And then it may need certain things, right? As you grow your application, it may need certain things that may be archaic, and that would kind of put your system to a specific system that needs to scale up to, and it is called an aging system, because you need it to keep it around. You may have to keep it around for a decade because you cannot find a suitor for it to be going up to. Think mainframes, right? If you're working with mainframes, where are you going to go next? So those kind of problems. Scaling out. One of the biggest thing about scaling out, and I talked about database sharding, was that you have a good distributed footprint, right? Which means you have the concept of high availability, right? So if that is what you need, then people scale out. But how do you know that I need to scale out? You have to look for the scaling factor. Again, measure, and not guess. The second thing is you could grow or shrink. So if I have, 5 nodes that I have current footprint on, and I know my utilization is not going to be needing all 5 nodes, then I can drop it down to 3 or 4, and I'll still be okay, right? Because again, it's a high available system, it's a distributed system, you'll be fine. And what is the con on that? Because now if I'm going from 3, I'm going to 10, now you have a higher footprint. And if you think about it in the cloud, where does all this thing go? It's in the data centers. So if you think about the physicality of these systems, you need to think about power, space, and cooling, right? So you're paying more money is what I'm saying, right? Even though you think you're getting a bigger system and you're scaling up, but even in scale out, you may have to go to the next rack, and that is more expensive, because of the physical constraints that it needs. So how do we scale? So I said measure, right? So let's do just that. So we're going to scale in the cloud for performance. So what I want to do is define some of the access that I have. So I'm going to show you some charts, and I'm going to talk about each of those. But before I go into that, remember I talked about capacity and utilization in performance? And here is what you see how I use them. So basically, scalability and performance go hand in hand, okay? So on the x-axis, you have the core counts in the chart. On the y-axis to your right, you have the scaling factor. And on the y-axis to your left, you have the maximum system capacity. What do I mean by core counts? Basically, what I'm doing is when I'm looking at the workload, I have a capacity planning workload that helps me understand the capacity of my workload, right? So what I do is I start from 2 cores, and I go up all the way up to the maximum system capacity for core counts, okay? And scaling factor, how does that help me? So scaling factor kind of shows me the demand. So again, I said the capacity planning workload does some work with respect to the threads and the utilization that tells me the demand of my workload, right? It highlights concurrency effects too. So when I am adding more worker threads, or I'm adding more users with respect to injection rate, for example, then I can see that more and more concurrent work is getting done. And it helps out. That's the number one thing that helps out with understanding if you can scale up or scale out. And I'll show you how. My capacity on my left y-axis, that is what is helping me to add more workers, like add more injection, like throughput. So basically, it's a measure of throughput, and The way we can do this is we can talk about the max, like that's the knee of your system. Or we can also define it in terms of SLA, so throughput under SLA constraints. So in this particular thing, I'm just showing you the max. And it helps with understanding, again, I said user requests, so whatever. So whatever your workload is doing, your capacity planner should be able to mimic that and tell you exactly the number of concurrent work that you're doing. Now with that, let's look at this graph here. So what you see here is incremental cores, like physical cores, your processing cores, from 2 to 96. And what you also see is this nonlinear curve, so in purple, right? So that nonlinear curve is showing how you're scaling with respect to the capacity. So that's showing your capacity at each node. What you see with respect to the scaling factor in green is basically a flat profile, right? So let's highlight a few things. With respect to your capacity, I already see at 32 core counts, I'm having issues. I'm not getting the maximum capacity, or at least it's not following the curve, right? So that is something that I would go investigate. What's wrong with concurrency right there? Or is there a contention based on your software? The other two things I see are this particular drop and then this drop. So with respect to my scaling factor, I can already see at 8 core counts, I have a drop. So I'm not getting this maximum scaling that I was getting. It was about almost 1.75 right there at the very beginning, but I didn't get that. And then again, towards the end at 96 core counts, unfortunately, I dropped down to 1.5. So my scaling is suffering. And that is probably because that's the way my workload is stressing, okay? And this is on Azure VM, and it's the Gen 2. So I'm just saying the names right now just so that you can keep in mind, because I'm going to compare it to a different one. So now you see a Gen 3. So I went to a better system, the next generation system on Azure, okay? And I see some different things here. I also see that the same scaling effects that we were seeing are gone. So now we don't have anything on 32. We have a tad bit of capacity issue on 48 cores. And you see that at 32, actually, we have a peak scaling factor. So we're about 1.8x at 32 cores. And at the end, towards 96 cores, I don't drop down, right? I'm holding it okay. So what does what do these numbers, what does this graph tell me? It can tell me if I can scale out, or do I need to scale up? And if I can scale out, how much can I scale out? Because we're talking about Java, we're talking about the JVM, I'm going to scale out with the JVM. So I'm talking about your software product, right? So JVM is my product, so I'm going to scale out with the JVM. So here's the comparison. Again, you have the Gen 3 system and the Gen 2 system. Gen 2 system is in purple, Gen 3 is in orange, right? I'm comparing single JVM, dual JVM, and quad JVM. So 1 is the maximum score that you get. And then anything that is less than 1, basically not the max throughput, then that's slower. So what I see here is that, remember my Gen 2 at 96 cores, it was dropping down, right? So if I did a single JVM of my Gen 2, I'm nowhere near the performance that I can get by scaling out. So if dual JVM and quad JVM are still better than the single JVM for Gen 2. Gen 3, did not have that issue at all. And of course, I can just use a single. So basically what I'm saying, in Gen 3, I can scale up to the maximum cores, 96. And in Gen 2, I should not scale up. I should scale out, either with two JVMs or just the 4 JVMs, which will be still better than the 1. Now, let's do some projections, okay? And this is the law. These are the laws that I was talking about earlier. So same graph. Like what happens when I try to get the trend lines, right? You have the nonlinear trend line that I showed you earlier. What if I just got the linear one? It'll look something like that, right? This is in Excel, just projections. Now if I added 5 more, I went on the x-axis, added 5 more data points. Excel tells me this is how it'll look. All right. What if I added 10? Again, Excel tells me this is how it is going to look. But are scalability projections that easy, right? The answer is no. that system cannot happen in real life, right? Even the nonlinear trend shows to be much better than my linear trend. So how do you do projections with respect to scalability? This particular graph probably looks familiar because lots of people use it. This is Amdahl's law. So what it's saying is that so Amdahl is funny because what they're saying is that a single core performance kind of sometimes is better. So you scale on single core. So scale out on single core, you will achieve better performance than you add multiple cores. And that is because of concurrency. Remember when at 32 cores, we had issue, and I was talking about concurrency issues. So it could be software, or it could be contention, and all those issues are present in your system. So Amdahl says that the more cores that you add, the more nodes that you add, then you're going to have problems, and you will plateau at the higher end. So no matter if you add, like right from 50 to 60 to whatever 80, you would still plateau. And that's Amdahl's law. But that's not quite true. So when we're looking at system models of, like, say, hardware, software, all these combination effects, we actually go and talk about a novel law, which is written by Neil Gunther. So it's called the Universal Scalability Law. So basically what it's showing you, the effects of coherency, and the effects of concurrency, and the effects of capacity. So those are the 3 C's that it's talking about. So here again, the comparison, linear, and then you have Amdahl's, and then you have Gunther's law. So these are the projections, and you can do this. Again, you can measure your these factors, right? You can measure your concurrency, the coherency, and you can apply to an equation, and that's how you do projections. Okay? Now, let's move on to a few other things that I wanted to compare and talk about how it's done with respect to Java. Okay? And by Java, I also mean OpenJDK because that's where most of the thing is, right? So we talked about, so at the beginning of this conference, we all saw the Project Amber, right? Where what you saw was like these kind of modifications that were made to the language, to the Java language, to make it better for humans, right? Like us. So first of all, how does a software get to be used by everyone? Like, how do you make it available to the masses? So, especially in Java's case, we always talk about write once, run anywhere, right? What does that really mean? It means that Java is portable, right? So how is Java portable? There is an OpenJDK porters group. People that work in the background, and Microsoft was one of them. So we did a port to bring Java to Windows on ARM. So we have OSs, different OSs, and we have different architectures. And what you see is the work of OpenJDK engineers like us. I'm not going to go into the details of the port and everything, but what basically it means, and I'm just explaining what a port means. It's when you have a new platform, like a new OS or a new architecture, you just need to make sure that the Java runtime environment, so people that run Java, they can run it on that system, okay? And what is a JRE? That you have the hotspot machine, the class libraries. The hotspot is the runtime, right? And it has an execution engine, like your garbage collector, the JIT compiler, all this fun stuff. And then you have the class libraries, which has the toolkit and the basic, Java lang stuff. And the JDK is a superset of all this and includes other tools and utilities for debugging. And to be able to, if you're going to write software in Java, then you need the JDK as well. So people that work on OpenJDK kind of help you do that. They port your stuff, port the JDK over to the new platform, and that's what gives it portability. What about usability? We were talking about Project Amber, right, here. And let's look at that a bit more. So basically, usability is the ability for anyone to use your product, right? So basically, your product should be user-friendly by the definition of user-friendly. So for example, if I told you, a garbage collector, that I can give you a new garbage collector, let's say G1 GC, and you just need to have 10, maybe 15 command line options, is G1 usable when you have 15 different command line options? And guess what? They change every time your workload changes. So you have to go figure it out yourself. Then that becomes less usable, right? If you look at the new garbage collector, ZGC, you just need to set the heap and then just tell it to use ZGC, and you're done. So ZGC makes it more usable, right? And that's the one thing about usability. The other thing is, think about error messages, null pointer exceptions. You know, they got better in JDK 14. Why are people so happy? Because it helps us be able to debug stuff, right? So things like that, that's usability. It brings a smile to your face. Project Amber stuff, you know, people may still want to be on Kotlin, and I hope not, because Java 19, right? There was a talk, right, that talked about Java 19 is going to make you forget Kotlin, I hope. But yeah, so that's, again, usability. And now that I talked about all, Java 19 and Kotlin, that is what makes it the user experience. So basically, it's the perception and the reaction to a feature. I welcome Java 19 because I have so many things to look forward to. So that is my user experience. All of that together is what constitutes the customer experience. It's about a journey, so you have various touch points in your life. So you talk to your customer first. You get the requirements from them, non-functional requirements from them. And then you say, hey, how are you feeling? Are we doing enough for you? Do you have the tools, the observability that you need, right? Do you have the happiness that you think you're going to get from this product, right? So I was talking about this presentation to a friend of mine, Alan, and just a second. So I asked, and I was discussing this, and he gave this awesome quote, right? He says, customer experience is the capability of your product, the reliability of your product, and the security that it can offer. Of course, Alan is SRE, like he's an SRE person. So of course, he can capture it in the best words that he can see. So I thought it was quote-worthy, and that's what you see here. Alan is a big fan of NFR, like non-functional requirements, and he was happy that I was talking about it. So as we come to an end of this conference, and of course this talk as well, I want to put it all together. And there's one theme that I hope you saw throughout the talks. It's about how do we become more efficient, right? It's about efficiency. So quality and efficiency go hand in hand. And I say that ilities, the qualities, the non-functional requirements, make us more efficient, right? And going back to the Miyagi quote that I said, John Cunningham is my Miyagi, is my mentor, and he gives me really good advice on many things in life. And I mentioned to him about this talk as well. And he said one thing to me. He said, yes, always do more with less, right? And what is that? That's the whole concept of efficiency. You're being more efficient when you can do more with less. Again, my beautiful pets, and if you have any questions, I will take them now. And please join Slido, and I will try to join it as well. Okay. Okay. All right. The first one is, which garbage collector is used in Oracle JDK? Used by default, I'm assuming. It is G1GC right now. It's the same thing. So the many JDKs out there, and Microsoft has a JDK as well, and of course AWS has the Corretto. And most often than not, they stay with the OpenJDK garbage collector. So if the default is G1GC and OpenJDK, because we all work together, we all work on OpenJDK. So that's where we push first. There may be times that you may have certain options, like say escape analysis, new features that are added by a particular company, and they may want to test it and stuff like that. So they may be a little bit ahead of some things internally, but when we deliver a product, and this is for anybody who delivers a product, we stay with OpenJDK because these are builds of OpenJDK, okay? And we try to push, like most of the companies have, upstream first philosophy. What are the possible differences between OpenJDK and Oracle JDK? Yeah, I don't work for Oracle anymore. I used to work for Sun Oracle a long time ago. So this question to me is that I know as much as you do, basically. But I could tell you about Microsoft JDK, for example. Again, we have upstream first philosophy, and we are experimenting with escape analysis. We did some kind of work with respect to providing vectorization work with respect to certain units. And so we have those things. We have pushed it to OpenJDK as well. So you may see certain things because we have preview features. So we're trying to provide that as well. Okay. What happened? Okay, so I'm going to go to the next question. There is always a lot to do and not enough time to do it. In your opinion, what's the most important ility to focus on? Performance, because that's what I focus on. Performance engineering is what I do it. And like I said, there's so many ilities that go hand in hand. Performance, if your user is not happy, is that, so their usability is suffering. Performance with respect, if you have no observability, then how can you measure performance? So things like that, all these ilities are hand in hand. I think performance is like one of the, and even availability, for example, falls under performance. So I think the giant umbrella is performance, so stay with performance. And come talk to me if you have questions. What happened to Visual J, Microsoft's Java fork? Good question. You should ask John Cunningham, all right? I'll let him know that you can ask that question to him. I wasn't there at Microsoft when that happened. Of course, I've worked on Sun JDK for such a long time. I didn't even think I'll be at Microsoft. But here I am now, and if you have time, I'll show you what Microsoft does with Java. We do a lot of things, and we're happy to be here. When we should start experimenting with different GCs? Ooh, good question. Like I said, what does the application's need, right? Are you looking for throughput, or are you looking for low latency? That's the way you go. You are right in the middle right now with G1GC, right? If you want to go left, go experiment with parallel GC. If you want to go right, go experiment with ZGC or Shenandoah. Actually, funny story is that Shenandoah started similar to G1, but it did a couple of things in more concurrent fashion and in everything. And now, where Shenandoah is, it's similar to ZGC with respect to self-healing nature, the read barriers, and stuff like that. So things converge. We just architected the garbage collectors, and I told you the stuff that is needed. So what do you think? It's not going to be that much different. In fact, ZGC is like Azul's C4. So you see the worlds are converging with respect to low latency, and of course parallel is where parallel is. You also have a low footprint garbage collector called Serial GC, which is sometimes really helpful at microservices. Think about that, single-threaded, gets work done out of the way, probably doesn't even need to kick off until you're done with your microservice or whatever, right? Or done with your results. Is it possible to predict scalability precisely? Good question. Prediction, again, my mantra is measure, right? If I cannot measure, how much can I predict? But I do like Gunter's law, because I was just trying to calculate that for the workload that I showed. And of course, I don't have, I think the maximum system that I was working with was 128 maybe. So I don't know after that. So yeah, so the prediction up until then was pretty correct. Now, when will you hit the knee? I don't know, and I hope it's closer to Gunther's law, I guess, or somebody else out there will come up with a new thing. Why are you using Mac? Oh, because, again, my Miyagi, Jock, the first day that I joined Microsoft, this was before COVID, so I was physically there in Redmond, and he showed up with a Mac because he knew that I haven't worked on Windows for a long time. So my background is Linux or Solaris, actually, and then Mac. And then recently, I'm doing Windows 10, 11, Windows Server. So Microsoft is cool like that. So I'm very thankful. I do have a Windows desktop, by the way, and that's where I do most of the work, but I travel with this one. How are your cats doing? That's my son. Thank you, sweetie. My cats are doing fine. By the way, we have a pet sitter that keeps sending me photos because Bowden wants to see them. So I have 3 kittens, and this is the first time we were leaving them alone. So, yeah. Great question on Java Flight Recorder. I think it's a great observability tool, right? It was missing for a long time, When we look, we have these kind of interfaces, like Visual VM is a good tool, right? And what it does, it uses these kind of MX beans interfaces, and we can read them, right? What was it, JStat, J something else. We had all these things that were doing these communications through MX beans. But when you compare what JFR tells you, because these are counters. So let's go back a bit. So your hardware, the way you know that you have a cache miss, like hardware cache miss, or your hardware prefetcher is not working as you think it is, or your hardware the pipelines are not working. You know that because your hardware has counters. So any kind of branch mispredicts, any kind of cache misses, you can count them literally because your hardware provides these counters. And these are called performance counters. And similarly, JFR provides that for Java, for OpenJDK. So it is an observability tool into your JDK. I say use it. There is JFR that you can stream. And there's lots of opportunities with JFR. Use it, give feedback to the OpenJDK community. And again, if you want to reach out to me, do reach out on Twitter. I am open to any kind of feedback with respect to performance, observability, any of these ilities that I mentioned here. Okay, I think that's the last question. Thank you so much. Thank you for having me here, GeeCON. Thank you for staying with me today. I appreciate it.